Thank you for joining us today for our co-hosted webinar with Scott Wrinkle and Eric Bogatin. My name is Lindsay Welch and I'm the Marketing Manager at TRS-RenTelco as well as the moderator for today's event. Just a few housekeeping items before we begin. Today's presentation will be part slides and part live demo. This webinar is being recorded and a copy of the slides and link to the video will be sent to all registrants later this week. We will hold the Q&A at the end of the webinar to keep us running on time. Feel free to submit your questions as they come up using the QA section of your control panel at the bottom of the screen. Ken Johnson of Teledyne LeCroy will facilitate the QA process after our presentation. For those of you just joining, today's webinar is titled 5 Techniques to Debug Power Integrity Issues Faster. Dr. Eric Bogatin will provide an overview and live demonstration of each technique. But before we turn things over to Eric, I'd like to introduce Scott Wrinkle from TRS. Scott is the West Regional Sales Director. He has over 25 years experience working for leading test equipment providers and excels at helping customers optimize their equipment procurement strategy to ensure they get the equipment they need with the financial terms that best meet the circumstance. We know your time is valuable and we appreciate you joining us. I'll now turn the presentation over to Scott.
Thank you, Lindsay. My name is Scott Wrinkle. I'm the Regional Sales Director for TRS-RenTelco. As Lindsay mentioned, I'm currently in my 25th year working with Teledyne LeCroy and our customers, many of which are well-known technology companies, to provide LeCroy tools that have been an important part of technology advancement. Mostly we help companies that don't have capital funds or your project timing doesn't allow you to buy equipment outright. Here are some reasons why. Capital is unavailable or takes too long for approvals. The project is short-term, usually under 18 to 24 months, or equipment is needed immediately. At TRS, we buy equipment so you don't have to and provide it back as a service, utilizing operating expense. This is what we mean by test and measurement equipment as a service. As a rental company, it's important for us to have availability, both equipment that you can get quickly and the availability to talk to a live person when you need help. At TRS-RenTelco, we respond to your needs and provide quick and accurate information for complex tools so you can get on with the task at hand. We then execute on our commitments, making sure the quote is correct, the equipment is correct, and the equipment is what you're expecting in good working order and calibrated. TRS is the only rental company in the United States that has 24-hour customer support. We are finding this to be even more important during COVID as folks need to stagger work shifts around the clock to meet social distancing compliance. I would now like to, next slide please. I would now like to introduce our presenter, Dr. Eric Bogatin. He is the Signal Integrity Evangelist for Teledyne LeCroy, Technical Editor for Signal Integrity Journal, and the Adjunct Professor at the University of Colorado Boulder. Eric earned his physics degree from MIT and his doctorate degree from the University of Arizona, Tucson. He's been a senior manager an engineer at Bell Labs, Raychem, Sun Micro, ANSYS, and Interconnect Devices. He started Bogatin Enterprises in '92, which was acquired by Teledyne LeCroy in 2011. And he's written 17 books, including popular textbooks and science fiction novels, which can be found on Amazon. I'd like to now turn it over to Eric.
Hey, thanks so much, Scott, for that intro. Welcome everybody to our webinar today. Now, before I go on, I want to introduce Teledyne LeCroy. We've actually been around for more than 50 years, headquartered in New York, where we do most of our scope manufacturing. Now, even though we're only the third largest worldwide manufacturer of scopes, we have a long history of introducing new products ahead of the pack. We were the first company to introduce digital storage oscilloscopes. And so you hear that term DSO, that was the term we introduced with the first digital storage oscilloscope, which basically is what all scopes are today. We introduced the first 100 gigahertz bandwidth real-time scope and 12-bit high bandwidth scopes. And what I'm going to be showing you today is some of our 12-bit vertical resolution high bandwidth scope technology. The name, so we've been started as LeCroy, and about almost 10 years ago, LeCroy was acquired by Teledyne Technologies, and that's why we're called Teledyne LeCroy today. Well, today's going to be kind of a quick whirlwind tour of a number of examples of not just using a scope, but using the combination of a scope, the right probes, and the right methodology in order to quickly extract useful information about mostly power integrity and power integrity problems with some digital systems. So I'm going to walk you through 5 different examples here of the power of that combination of high performance scope, the probe, and the best measurement practices. Well, let's get started. And first I want to introduce you to our scope that we're going to be using today. We have a family of 12-bit scopes. These are the high definition scopes. The one in particular we're going to be using is this guy over here. This is the Wave Runner. And the Wave Runner is this particular one. So here's the 8208 HD. Here's the decoder ring. The 2 means 2 gigahertz bandwidth, and the 8 means 8 channels. So we're going to be using an 8-channel scope, and I'm going to show you an example right off of how 8 channels can give you a lot more insight into what's going on in some of your digital systems. This one is a 2 gigahertz bandwidth, 12-bit vertical resolution all the time. So let's get started. And I wanted to start out this first example looking at a specific problem, and the problem is about measuring switching noise in your system. And to do that, I'm going to introduce you to a trick that is really, really useful, and I don't think it's very widely known, that will help us get a handle on kind of a window into what's going on in your device. And here's the trick. And it has to do with, I'm going to show you the difference between measuring the voltage noise on the board or at the board level versus the voltage noise on the die itself. Because what the active device cares about, where the noise plays a role, is on the die itself, not on the board. And there's a big difference. And here's the trick we can use to measure voltage noise and ground bounce noise on the die. We take advantage of the IOs that are on the output. And in particular, I'm going to show you a couple of examples of different systems where we can designate the IOs as either what is referred to as a quiet high or a quiet low. And all that means is the output is pegged either to the low voltage side or the high voltage side, depending on what the input is. We can do it in hardware, that's the first example, or we can do it by microcode, and that's going to be the second example I show you. And so we set an output always at low. That means that, if it's a CMOS kind of output driver, that means that the N channel, if it's output low, the N channel is basically on, and that means the output pin that we look at with the scope, that output pin is tied to VSS on the die itself. And so when we look at the output pin with the scope somewhere off on the board relative to a local ground, we're basically going to be measuring the voltage noise everywhere throughout that loop, that victim loop. And that's going to rise from switching noise on the die, switching noise in the package, switching noise on the board. And we're going to look at how that varies in a couple of situations and how the layout of the board influences it. If we peg the output high, then the output is going to be tied to VCC on the die. And when we look at that voltage on the output pin, when it's pegged high, it's telling us the voltage noise on the VCC pin on the die. And what we're going to see is that voltage noise can be very different from the voltage on the power rail on the board. And in addition to looking at the IO, so we get an idea of what's going on the die, we can use this technique anywhere. It's basically, we're looking at crosstalk. And in particular, when we have a screwed up return path, the nature of that crosstalk line with a shorting via to the return path, and we look at it somewhere with our scope, and what we're measuring is the voltage noise on that path, the crosstalk on that path. And so I'm going to show you how we actually implement that and how we interpret the results. And to do that, I'm going to bring you into my lab, and I'm going to show you the board that we've got. So here is my lab. Get a little camera here. Hi guys, and I've got a little board set up. This is a board that actually I use in one of the classes I teach at University of Colorado in Boulder because it illustrates good and bad layout technique. But it's a really simple board. Now I've got it instrumented already with all the cables here going into my Wave Runner 8208, and I'm going to pull back a little bit so you can kind of see what's going on here. And unfortunately, it's a pretty crowded system here, and you really can't get in the scope very well and be able to see the board. And so it turns out that our scope is running Windows 10. It's got a 4-core. It's got 3.6 gigahertz clock. It's got a 36 or 32 gig of RAM. It's got half a terabyte hard drive. It's a computer. And because it's a computer, oh, and it's got all these really fast high resolution A to Ds in the front, so it's a really fast scope as well. But because there's a computer underneath it, I can run TeamViewer on the scope and on my laptop so you can see the screen. So let me walk you through the board, and then I'm going to show you some of the measurements from this board. So let's take a look at this board. I'm going to zoom way in. It's a really simple board in this case. We've got a little oscillator over here. It's a clock. It's going to drive a couple of hex inverters, and I've arranged, because a hex means 6 outputs, I've arranged one of them as a quiet high, one as a quiet low, one as a trigger, and the other 3 are going to drive some currents on these LEDs that we have over here. In the bottom quadrant, I've laid out the board really well. I've got a nice solid return plane underneath, and so I've minimized the ground bounce that I expect to see in this board. In the top quadrant over here, I don't have that nice wide return plane. I have individual return paths, and so we're going to absolutely guaranteed see a lot of ground bounce. And we're going to look at the difference between them. So the first step is I've got an output over here that's one of the I/O switching, and we're going to look at that into the scope. Now I'm going to plug it in. We'll turn it on. There we go. I always tell my students, add indicator light so you can tell at a glance what's working and what's not. So we got the we're going to look at the trigger coming out of this guy. So let me show you my scope. And it's a trigger. It's just going to turn on. It's got like a 500 hertz clock or so, something like that. And here we are. Here is the measured voltage in channel 1, which is the trigger output. And you can see it's kind of a funny kind of a signal. It's 3.3 volts coming out eventually, but it's got a little bit of ringing in here. How come? Well, the output impedance, I'm going to see if I can do a split screen here so we can see both of them. Here we go. The output impedance of this driver is relatively low. It's about 20 ohms or so. Of course, is 50 ohms. And in the scope, let's see. Here we go. Here's channel 1. In the scope, I have the scope set up for 1 meg input impedance. That's a recipe for ringing noise. I've got a low impedance from the driver, 50 ohm cable, 1 meg. Any fast edge that gets in there is going to be bouncing back and forth. We're going to get ringing. And how do you eliminate that? That's where 50 ohm termination comes in. So I'm going to set the input coupling instead of 1 meg. I'm going to set to 50 ohms and watch what happens to that ringing. Wow, all gone. Now we're seeing the true rising edge of the signal coming out of our device with no reflections. And, you know, I've got a little parameter measurement tool over here. It's a little under 2 nanoseconds as the 1090 rise time. That's what we're starting with. Now we're going to look at the voltage noise on the board. And so over here is going to be that little test line I mentioned that's just going across the board. It's shorting to the ground plane underneath. And so that's going to be a quiet line that is just sensitive to crosstalk noise. So let's turn that one on. Now, I've got 8 channels here because there's so much to look at. It's way over here. I'm just going to drag it over here. So our scopes have generally 3 ways of interfacing. There's the, it's a touch screen, we've got menus, and we got the normal knobs. And in order for me to show you what I'm doing, I'm going to use the mouse interface on the screen itself. But everything is touch screen, and literally to move a trace over, all I did was drag the little icon and click the icon, drag it over, and move it in. Here is the voltage noise on that quiet line. So we're looking at the voltage noise over here, the crosstalk. And look at that. oh my gosh, there's all this ringing noise. First, there's noise, 20 millivolts a division. There's noise, not a lot. You know, it's like a 2 volt, 2.5 volt signal, 20 millivolts. So, you know, we're talking about 1% kind of per division noise, but it's got this funny signature. How come? Once again, always pay attention to the device under test. The output impedance of this line is really low. It's a short. And so I've got a low impedance source, 50 ohm cable, 1 meg in the scope. Of course, this is all reflection noise. It's an artifact. We don't want to see that. That's where 50 ohm termination comes in. This is the voltage noise on the board itself. This is some real ringing because of the size of the trace and the capacitance in the vicinity. But the voltage noise is 20 millivolts, not much at all. Let's take a look at the quiet low on the device itself. Let's see, that's going to be in channel 3. And now that we know to watch out for this ringing problem, I'm going to make sure that I have 50 ohm termination on all the lines. So let's drag that one over here. This is the voltage noise on the low side of the device. So this is really telling us we know. In fact, let me go to the same scale. I'm going to adjust the scale to be 100 millivolts for each of them. The noise on the board is really small. Here it is in pink. The noise on the package, or the noise on the die, is, you know, quite a bit more. It's 100 millivolts per division. So we're talking about, you know, plus or minus 200 millivolts or so. That's a lot of noise. It's not about the board. It's the package noise, because we're showing you the voltage noise on the board is pretty small. I'm going to zoom out a little bit so we can see that a little bit better. And here we see a tiny bit of noise on the board, a lot of noise in the package. This is ground bounce because of the package leads. Now, this is the case for really good layout. Best you can do. Nice return plane. I've also got the other quadrant up here that has poor layout, and we'd expect a lot more ground bounce. Let's see how much more. So I have in channel 5 over here, I think, I have the ground bounce on the board in the bad layout region. Let's grab him and move him over. Oh my gosh, this is the ground bounce on the board itself. This has nothing to do with the package. This is a dummy line, a sense line on the board. Huge amount of ground bounce. Look, 100 millivolts a division. That's 1, 2. That's almost 400 millivolts peak-to-peak noise on the board. Any trace on that board in that region is going to show that much crosstalk because of the poor return paths. And we do the same thing. We look on the package, and here we are in 6. We'll look at the package noise, and you can see the package noise just about the same as the board noise. Yeah, we have this same amount of package noise, but it's hidden inside the board noise. A lot of ground bounce noise because of poor layout. Well, this is looking at ground bounce. Now we're going to look at the power rail noise. The problem with power rail noise, I'm going to go back to the slides here to kind of illustrate the problem with power rail noise. We have to be really careful. We already showed how important it is to use 50 ohms to avoid the reflections when we see transients. The problem is when you look at power rails, you want to be careful about putting 50 ohms on there, especially when you have a low current source, because that 50 ohms is going to load that 5 volt rail. You got some other problems when you measure power rails as well. You're sensitive to, depending on the probe, you want to use an RF or a coax connection to avoid pickup. Because we're going to look at small voltages, you want to avoid a 10x attenuating probe. You don't want to load the line down, the rail down, so you want a high impedance at low frequency, you want to be able to offset, and you want high bandwidth. Really hard to do that with a conventional probe of any sort. That's where active probes come in. And there's a whole generation of active probes called rail probes that are literally designed specifically for power rails. And so in my scope here, I'm going to zoom out and show you. In my scope, when we look at the power rails, I've got some rail probes connected, and these are going to be measuring the quiet high and the 5 volt rail on the board. And let's just take a look at one of these measurements. So here's the, when you got 8 channels, boy, there's a lot of information. Being able to manage that information, display what you want, is really important. So I'm going to move out these signals that we were looking at that was just about ground bounce, and now we're going to switch our attention to power rail bounce. And so the first one we're going to look at is the quiet high on the good guy. This is going to be a 3.3 volt rail we're going to look at a small switching noise as we draw this about 100 milliamps of current. So let's look at him on channel 4. And here he is. So here's our 3.3 volts. When the IO switch, and we get a lot of current drawing, look, this is that switching noise signature. And the rail probe is automatically adjusted with 50 ohm impedance at high frequency, high impedance at low frequency. And so this is not ringing, this is the real voltage noise on the die itself. Now, while we're doing that, so look at the number. I mean, this scale is 100 millivolts per division. We've got a 200 millivolt drop out of 3 volts. So, there's our, roughly 6, 7, 8% voltage drop switching noise just when these IO are switching. This is what's going on die. If you measured the voltage noise on the board, so here's our board again. This is our 3.3 volt LDO, doesn't supply a lot of current. We're going to look at the voltage noise on the board, and we're going to compare that voltage noise on the board with the voltage noise in the die itself. So let's see, that is, I think that's channel 8. So let's bring it in. Here's channel 8. Look at this. It's hard to believe, but they are actually on the same scale, 100 millivolts per division. The orange trace here, this is the voltage noise on the LDO, on the board. Can you see? I can't even see the noise on this level. It's a tiny bit of noise. If you had just gone ahead and said, I'm going to measure the voltage noise on my rail, that's going to tell me how much switching noise I'm going to see. And if you went and measured, you say, wow, that's great. I have no switching noise. But that's not telling you what's going on the die, because it's those capacitors, the decoupling capacitors, that are filtering that switching noise on the die, getting on the rest of the rail. It's only by measuring on die that we're going to see the actual switching noise, which is a form of power rail crosstalk to all the other IOs. This is switching noise. This is what we're trying to minimize by using decoupling capacitors in close proximity to the IC. Okay, and here's this is also an illustration of, I'm going to zoom out so you can see my system here. There's a lot of information that we're having to manage here with all the IOs coming off the board and being able to measure them all at the same time, because they're all about switching noise. So we want to see them all synchronous with the IO that switches. Okay, first example, the power of probes and having a lot of channels on the scope. It gives you that extra window into what's going on. Now I want to switch gears, and I want to show you an example of the very conventional and very popular 10X probe. This is a probe that ships with every single scope. It's in every single lab. It's the first probe that you grab when you want to do a measurement. And I'm going to show you a really important artifact to watch out for when you use a 10X probe. And so again, I'm going to bring you into my lab, and we're going to look at another board. This is a microcontroller board, another board that my students have developed. Let's see. So let me bring you into my lab. So here we are in my lab, and I've got a 10X probe here. Here's the 10X probe. It's plugged into the scope here, channel 1 in the scope. Here's the board that we're going to be looking at. And I'm going to show you, so I've written that this is a case where we can engineer the IO by writing the microcode. So I wrote the microcode to have a couple of IOs switching. And I'm going to use this 10X probe as you might normally do. And we're going to look at some of the signatures of this noise. So we're going to look at the output pin over here, and here's the signal pin. So we got a ground connection, we got the signal pin. We're looking at one of the IOs that are switching. And let's turn on the scope, and let's see what it looks like. Now, this is roughly a 5-volt rail. And so we ought to see something on the order of about 5 volts as the output, and it's going to turn on pretty fast. It's actually about a 3 nanosecond rise time signal. And here it is. Here's the output. Now I'm going to change the trigger. I have the trigger on auto. It's not coming out often enough, and so we're getting some auto triggering going on. I'm going to switch the trigger to normal. And now it's only going to trigger when that trigger level comes in. And you notice that signature, oh my gosh, it's got some funny behavior. Where is that coming from? Now, just for comparison, I'm going to save that waveform, and we're going to compare it. And we're going to put into, and I want to I want channel 1 information into memory location 1. So we're saving that. I'm storing it over here on this side, and we'll do it for comparison. But just so you can see, yeah, it's the same waveform. There it is. We're going to store it over here. This is the waveform that we're measuring when we have the normal configuration for these long leads. Now, that by itself is a concern. I'm going to show you the difference when we do it the right way. That's concern number 1. But there's a bigger concern, because in addition to increasing the loop inductance in this path where the probes are, and then distorting the signal, we're also creating an antenna. That's why I always say there are 2 kinds of engineers: those who are designing antennas on purpose, and those who aren't designing them on purpose. And whenever you pull the signal away from the return path, you're making an antenna. But you can say, well, wait a minute, this is a 10x probe. Isn't it like a meg impedance? Isn't it really high impedance? You got to have current in an antenna in order to radiate. How do you get current? It's high impedance. Well, at DC, it's high impedance, but that's part of understanding your equipment. That's what we call it situational awareness, being aware of the electrical properties of your system. This the equalization circuit. And so we could get milliamps of current, especially for a fast edge. We can get milliamps of current circulating in that loop. It's radiating. The impact of that is if we have another 10x probe, so here is another 10x probe, and we happen to be doing a measurement nearby. For example, we're doing a crosstalk measurement. We say, hey, how much crosstalk is there from another pin over here? If we just bring it in vicinity, look, all I've done, I've shorted the ends. We should have 0 volts there. I'm just going to leave it in proximity here. And now let's look at channel 2. Channel 2 is where I plug the probe in. Here is the signal in channel 2. And I'm going to split the screen so we can see it again. So look, as we move it far away, we're getting less pickup. As we move it in proximity, oh my gosh, look at all of that crosstalk that we're picking up. We're picking up, 100 millivolts peak to peak of crosstalk noise just because of this probe itself. Just because this 10x probe, the process of doing the measurement is increasing the noise. And so we want to be careful when we use a 10x probe. Number 1, don't use large loops, because that means you're going to have distorted signal. And number 2, that also means you're going to have RF noise generated in the vicinity of your probe. And that's why every 10x probe ships with these tiny little spring ground tips, so that we can make a very, there it is, a little spring tip, so we can make a really low inductance connection to the tip. And I'm going to connect this in, and I'm going to show you what that signal looks like when we do it that way. So the 10x probes, the caps pull off, and when the caps pull off, you can see a little shield here. This is the ground connection. Here's the signal pin, and we literally just wind that little spring around, makes contact, and now we can probe. And now we have to get the right pins here. And now we can probe. Did you see that? This is the measured voltage coming out of that pin using the low loop inductance path. Now, just for comparison, let's move our stored signal there. Remember, this is what we measured with the large loops. In yellow, the live signal, that's what we're measuring now with the short loops. So you always want to try to avoid long loops with the 10x probe. Number 1, it distorts a high-speed signal. And number 2, it generates a large loop and radiates, and that's going to give you crosstalk artifacts when you come along with another probe to do measurements. And so that's why short ground leads and using those little spring tips are so important. Key trick in using 10x probes.
If you want, I have it muted.
Now we're going to take a look at another example, and this example is going to be looking at the current draw in a power rail. Now, I've got this particular board here that we've been looking at. I've got this board that I've instrumented with a series resistor in the power line so that we can measure the current draw through that power line. And let's take a look. I'm going to show you that. I'm going to show you the probe again so that we can, or the board so we can see it again. And let's take a look at our picture here. So here is the board. Let's see if we can get a close-up of it. Now this board, if you look closely, let's see if we can zoom in and get a good close-up for you. This board has a little series resistor here. Power's coming in on the USB line over here, and it's got a little series resistor here, about 0.5 ohm series resistor, and that series resistor, all the current's going to flow through that series resistor, and in flowing through that series resistor, we're going to get a voltage drop based on the current flowing in the power rail. And so we've got a couple leads coming off to the side here so that we can pick off the voltage across that 0.5 ohm resistor, and it's on the 5-volt rail, and that means that, oh my gosh, it's sitting at 5 volts, and we want to measure a small voltage across it. We want to measure the, it's about 5 volts and with a 0.5 ohm, and if you're 100 milliamps, we're talking about 50 millivolts. We're going to be looking at a 5-volt signal on one side and 4.95 volts on the other side. You can't use single-ended probes to measure that. You have to use a differential probe. And so I've got one of our differential probes here that we're going to use. And before I put it in, I want to drive some more current. I want to see some real current flowing through this board. And so I've got this little shield that, again, one of my students made for us that is going to drive some extra current. And so we're going to plug this guy in, and that's going to give us more current. Here we go. So here's our little board. You can see it's got a bunch of IOs that are switching. We got the LEDs here to show you the current flowing through those LEDs. I'm going to use my 10x probe to look at the current through one of those resistors so we can see how fast it's turning on. And then we're going to look at the current in the board. So let me get the scope going here for us. So here's our camera. Here's the scope. Now we don't need the saved image. I'm just going to drag this off to the side. I don't need that channel yet either. So here is the current through the rising. It's turned on relatively fast. And now we are going to look at the current flowing through that 0.5 ohm sense resistor. So here's our board. Now this particular differential probe that I'm going to be using here, again, because it's a differential probe, it's an active probe. This particular one is a more sensitive probe, but it's only a 500 megahertz bandwidth on it. We have a new probe we just came out with recently. That's the DL10 HCM. It's a 1 gigahertz bandwidth probe, and it has a 60 volt common mode rejection on it. This was only a 50 volt common mode rejection. And we're going to come along here, and we're going to, here's our differential probe. We're going to plug it in, and we're going to measure the voltage across that resistor while the IO is switching. Plug it in. I may have to flip it around. Yep, there we go. Okay. And let's see. So we plugged it in, and I'm going to show you the features of that probe here. Here we go. Now I'm going to go ahead and while it's not plugged in, I'm going to auto zero it so we kind of center it. It's disconnected, it's auto zeroed, and now we're ready to go. So let's move that voltage over here. And now we're going to look at that differential voltage across the 0.5 ohm resistor. And let's plug that guy in. There we go. Okay, now not a lot of currents going through that that resistor here. Let's zoom out just a little bit on the scale. In fact, you can see the current that's flowing through there. It's kind of a steady, constant amount. I don't see that large current flowing through there. Let's slow down the edge a little bit, or zoom out a little bit in time. And now you notice, oh my gosh, look at that. There's a lot of current flowing through the power rail, but look how slow it is compared to the current draw through the I/O. The I/O are drawing a lot of current over a very fast rise time. Oh my gosh, we don't see any of that behavior until we zoom out in time. Look, here's this is 200 microseconds of division. There's about a 200 or 300 microsecond time constant for that current to turn on. How come? This is where, again, we're opening up a new window into what's going on with our board to understand how that board is actually working. It's because of all of those decoupling capacitors that we have locally where the I/O are switching. It's all of those decoupling are coming from locally, the decoupling capacitor, and this slow rising signal here, this is the current coming through the USB in order to charge up those decoupling capacitors. And that says they're doing their job. They're keeping the high frequency currents off the board, and they're providing the local charge for those fast I/O. Now, while I'm here and we're looking at the current through the board, there's one other really important measurement that we can look at using this technique of measuring the voltage across a sense resistor while we're running the code. Because of the filtering of the decoupling capacitors, we're not going to see really fast microcode changes and its impact, but one of the important measurements we're going to do is the inrush current. So I'm going to, we've got it set up here, we're measuring the voltage. I'm going to zoom out in the voltage range. So here we go, we're zooming out. We have a very wide dynamic range because we can change the we can change the gain and the attenuation automatically. It's a smart interface with the scope. So we have a very wide dynamic range. I'm going to zoom way out because we're going to look at inrush current. And so to do that, I'm going to first unplug the power to the board. And then we're going to look at how much current flows when I plug it in. So here we go. I'm going to unplug it. It's unplugged. We have no more current. Now, I want to trigger the scope on the inrush current, on that voltage based on the voltage across that half an ohm resistor. And so I want to trigger on channel 2. So here we go, trigger on channel 2. And because I know it's going to be a lot, I'm going to set the trigger here. I'm on normal mode. So the scope is only going to trigger when I get a voltage coming in. And I'm going to, oops, I'm gonna change the time base, zoom out just a little bit. And now let's plug it in. So I'm going to show you when I plug it in. So what we're doing is we're plugging it in. We're getting all that current coming from the USB port that's going to have to charge up the capacitors on the board. That's the inrush current. Let's take a look and see how much we've got. So here we go. I plugged it in. Did you see that? The pink is the current, the voltage across that half an ohm sense resistor. Here it is. Look, here's 1 volt. Here's more than a volt. If it's a volt, that's 2 amps of inrush current coming from the USB. Second time constant for charging up the capacitors on the board. This is, again, a little insight into what's going on in your board using this new kind of a probe, a new kind of probing technique in order to open up a window into what the inrush current is doing on your board. Okay, and let's return to the slides. And let's see the slides. So the next experiment we're going to do is looking at the common radiated emissions from a board. And so I got our board turned on, and I'm going to show you a new kind of probe. So let's go back to the picture we got here. So when you look at near field emissions are not quite the same as far field emissions. Near field emissions, if you have near field emissions, it's no guarantee that you're going to fail far field emissions like a FCC certification test. However, if you fail an FCC certification test that says you have far field emissions, chances are you're going to have near field emissions as well. And so we're going to take a look at, I'm going to go back to auto trigger here. We're going to take a look at a near field probe. Here it is. It's going to be sensitive to the near field magnetic field radiation from the board. And I'm going to be looking at the near field emissions synchronous with the I/O switching, where I have a lot of current. So let's go back to our configuration where we trigger on the signal coming out. So here is that signal coming out. We'll go back to our normal mode. So here we are, we're triggering on the I/Os that are switching, and I'm going to zoom out quite a bit here so we can see it in a little more detail. So we're triggering on the I/Os that are switching. So this is where that I/O current is. And now while we do that, we're going to look with our near field probe at the emissions. And let's go to a sensitive scale. And let's see. So here we are. Now I need to show you what I'm doing. So here's the board, here are the I/Os. When we get in close proximity, now maybe if I zoom out in time, that will help you see that a little bit better. We'll zoom out in time. When I'm in proximity to where the I/O currents are switching, they're flowing over the surface, I see the near field radiated emissions. And you can see they occur when I have the I/O switch. That's what you'd expect to see in surface traces. If I look at the board, however, you're going to find, oh my gosh, I'm looking underneath the board. There's a lot of I/O current switching. And if I go elsewhere on the board, oh my gosh, look, we're seeing something else going on. We're seeing clock edge noise. Doesn't mean the clock is radiating, but what it means is there's some other source of near field emissions at the clock frequency due to the core logic switching, probably in the power distribution path. And so by looking with the near field probe, we're able to pick up not just the I/Os that are switching, but also from other sources, predominantly in the I/O. Now I'm going to show one last measurement here while I have this. I'm going to look in the bottom of the board. And you notice on the bottom of the board, you don't see anything, absolutely nothing. And that's because this board, the microcontroller board, was designed correctly with the nice continuous return plan. Keeps the return currents in close proximity to the signal currents, no radiated emissions. But while I have this set up here, I'm going to show you an example of another board, exactly the same microcontroller board, designed, a commercial board that was designed that wasn't designed with nice, good return paths. And here's that board. It's a commercial board. I've got exactly the same shield on top of it, drawing the same current. We're going to look at that, the current with our 10x probe. So we trigger the scope with it. So there's our signal coming out of this microcontroller. It's exactly what we saw before. But now let's look at the radiated emissions. Near field, okay, that's just about our shield, about the same. Here's the board level emissions. You know, kind of about the same. We see both the clock edge noise. We see some of the I/O. Oh my gosh, we got a lot of additional noise going on. But let's look underneath the board. So now we're underneath. And now, can you see all that near field emissions? The large area of the ground planes on the bottom of the board are radiating like a banshee in some places here. That's what's going to cause far field emissions. And that's where you can gain a lot of insight about near field emissions using a little probe and a sensitive 12-bit resolution scope in order to see those small emissions. Doesn't mean your product's going to fail FCC. What it does mean, though, is, oh my gosh, you get a lot of near-field radiation. There's a potential, especially if it's over a large area, like these poor return planes on the bottom of the board, high probability that that will cause a problem. Now, I wanted to look at one last problem here. So we talked about radiated emissions. There's another source of radiated emissions, and that is from common currents. And one of the most common sources of common currents is in the power cables, and it has to do with how the grounds are connected. Well, I don't need to look at the signal coming off the board anymore, but instead what we're going to do is we're going to look at how much common current do we have coming off of the cable. And so I'm going to use a current clamp that's going to measure for us how much common current is in that cable. In this example, this is just a little microcontroller board. It's sitting here minding its own business. It's running away. We got a lot of stuff switching on it, but the power comes from the USB hub connected to my computer. Now I'm going to plug in. We're going to use, so I'm going to show you again my setup over here. I'm going to use this is one of our current clamp probes. It's really a Hall effect probe. It's a current clamp, and it's got on the inside here, it's got a ferrite core, high permeability core. Any current going through the probe generates a magnetic field that is kind of accentuated by the ferrite core, and there's a Hall effect sensor in the middle of it measuring that magnetic field. That means that even DC currents that generate magnetic fields, we can measure. So I've got it set up here. I'm going to go back to our auto trigger mode here. So here it is, and I'm going to clamp it. I'll show you the picture of what we're doing. I'm going to clamp it around the cable, and we're going to measure, well, how much common currents do we have going through the power cable? So I don't know if you can see it, but I didn't see any change. We're looking at, wrong channel. That's why we didn't see a change. Let's go back to channel 1 here. Here we go. Here's channel 1. Now we're looking at the current coming out, and I'm going to zoom way out here. Now here, I'm going to unclamp it. I'm going to move it away here. So it's unclamped. Now I think what I'm going to do is, it has a little offset. So I'm going to degauss it and auto zero. So I want to show you my scope probe here. Let's see. Now the scope probe is so I've clamped the scope probe. We're going to degauss it. So we've got it all set. We're degaussing it and we're auto zeroing it, and that's giving us the auto zero for it. And then we're going to measure the common current going through the cable. Here we go. So very little current, nothing going through it. Now we're going to clamp it on the outside, and you can see, okay, you didn't have to blink there. There's no change, no common current going through there. So now what we're going to do, let me see if I can get my camera back here. There we go. Get my camera going. So now what we're going to do is we're going to change where the ground to the board is connected. And so watch what happens when I connect the ground of the board to another source of ground. Oh my gosh, let's slow it down so we can see all the things going on here. We're going to slow it way down. So we're going to see low frequency noise. So all I did was connect the output shield of the USB, which is the ground connection. I just connected to another ground source. So they're all ground, right? Everybody's plugged into the power rail, or the house in the lab here, the the neutral line in the lab, they're all connected in there, and yet, oh my gosh, we're seeing this large amount of common current, 100 milliamps of common current in that cable. And if I go to another source of ground somewhere else, I can see another amount of noise on that. Let's try another source of ground here. Oops, go over here, and let's get another source of ground. Hey, here's another device. They're all connected to ground, but because of the slight ground voltage difference, when I connect ground from different instruments together, we get ground loops. And those ground loops can get a significant amount of current, and those currents are what are going to radiate. They're common currents. That's what's going to radiate and fail conducted emissions tests. And so that's where these common currents are really important to measure using these common current clamps. Okay, so let's get back to the slides here. And I've got to the slides a little bit here because of the slight complication with my monitor. Let's see if we can get the slides back. And so I may be having a problem here getting the slides back from the monitor. So let's see. Do you think that, hey, Scott, do you think that you can turn on the slides from your computer and share your screen?
Yeah, let me give that a shot, Eric. Thank you.
Okay, and that's just as well, because we just finished the last example that I wanted to show off. And so, Scott, I'm going to get you to share your screen.
Great, 1 second here. Okay. And by the way, Eric, excellent presentation. Thank you very much. Let me go ahead and share screen. Go ahead and get into slide. And one of the things we're very proud at TRS is we do have an exclusive relationship with Teledyne LeCroy to handle the rental of all the scope lines. And so we saw that the rail lines, HDO, and the Wave Runner oscilloscopes mentioned today. We also support the SDA line of higher line products. And then we also have protocol tools protected. We support and we ship all this out of our Dallas Fort Worth location, right on the DFW airport. And we have all our metrology, calibration, repair, and service. For this event, we have a special webinar offer where we're offering free digital power management software for the scopes that were mentioned today. And then we have the scopes as well as the probes. And then we also have the SDA series scopes, which are going to be our higher performing products. And then we offer the full suite of software associated with that product as far as free with the rental. So that could save you lots of money. And then we also have a lease program where if you needed to own the equipment, we can lease it to you for 12 or 18 months, and we provide the last month free along those lines. So with that, I think we're ready to turn it over to Ken.
Yeah, so we can take our questions now. So we have a few of them queued up. First of all, a few people have said thank you, Dr. Bogatin, so for a great presentation. And let's go to the Q&A. Eric, the first question is, what would you see if you summed the quiet low and the quiet high, which is what the die sees for power?
Right, a very good question. And so that measurement is called rail compression. And Paul, who's asking that question, is exactly right, that what you see is the voltage on the VCC on the die and the VSS on the die itself. by taking the difference between those two. And it turns out that when you do that, and I apologize, we just didn't have time today to show that, but when you do that, that's an important measurement to take a look at. What you find is that there's still substantial amount of noise voltage, predominantly because the ground bounce noise is typically larger than the power rail noise. Depends, of course, on the decoupling. But that's a really sensitive measure of, you know, the relative balance of the inductance of the paths on the power rail and on the ground rail. And so that is a really important measurement to do. And that's why, you know, all of our scopes have math functions built in, so you can literally look at the difference on the VCC and the VSS on the board.
Okay, good, good. And if that's a person who asked that question as a follow-up, please type it into the Q&A pane and we'll try to get to that. The second question is, how is the active rail probe different than a 50 ohm coaxial cable probe?
Right. So really good question. We actually have a webinar series that we've done about power integrity measurements, and all of that's available on the Teledyne LeCroy website for events. They're all free, they're on demand, so you can get a lot of more information from there. But I'll give you the 30-second answer. If you use a 50 ohm connection to a rail, you're automatic. You know, the good news is, hey, you got 50 ohms and you're eliminating the artifact of reflections. That's great. The downside is, gosh, number one, with 50 ohm input, you're limited to no more than 5 volts because of power consumption in that 50 ohm resistor. You can't exceed about half a watt of power consumption. Otherwise, you can thermally damage that calibrated 50 ohm resistor in the scope. So never ever plug in 50 ohm cable with 50 ohm in the scope to a voltage, a DC voltage or RMS voltage greater than 5 volts. Problem number one. Problem number two is, if you're looking at a 3-volt rail that can drive, you know, 10 amps, it's a who cares. 50 ohms in the scope, great idea. But if you're looking at, in this example I showed here, if you're looking at an LDO that can't source more than 100 milliamps of current, when you put 50 ohms across 3.3 volts, that's 60 milliamps. That's most of the current rating of the LDO. So the process of measuring the voltage rail, you're going to be distorting what the rail is doing by drawing so much current. And for looking at the IOs, their output impedance is in the order of 10, 20 ohms. And so when you put 50 ohms across the LDO, you're kind of shorting out the LDO or the voltage rail on the die with that 50 ohms. And so you're distorting the measurement. When you measure a power rail, a low current power rail for IoT kind of applications, microcontroller applications, you want to be really careful not to draw too much current to distort the measurement that you're seeing. And that's where having high impedance at low frequency is so important. But at the same time, low impedance or 50 ohms at high frequency to prevent the reflections. And that's part of the magic of what the active rail probes do, is provide that impedance that's frequency dependent, so it doesn't load the rail down at low frequency, but gives you 50 ohms at high frequency so you can prevent the reflections. And it does some other things too. It gives you a good offset capability. This rail probe that we used here is capable of up to 30 plus minus 30 volts of DC offset. And so you can look at really small voltage levels with a very large voltage offset on the rail.
Okay, good, thank you. Okay, next question is really a request for you to repeat something you showed earlier during your camera live demo.
Okay.
Can you please show again how to connect the ground properly to the 10X probe to avoid a large radiating loop? So I think it was the connection of that.
Okay, so here's what I'm going to try to do. I got my camera working here.
Okay, and I think we need to arrange for you to share again.
Yeah. Okay, and now I'm going to share my screen. I've got that camera there. Here we are. Okay, can you all see my camera view over here? Here I am waving to you guys here.
Yep.
Okay, good deal. Okay, so here is the 10X probe. Now, in this 10X probe, I pulled the cap off, and there's this little spring end that just kind of unwinds, and I've still got the long ground lead connected here. If you plan to do a lot of measurements of the spring tip. This unscrews, the tip unscrews, you can pull off the ground lead. Otherwise, it's a who cares, just flops there. Because when we take that little spring, it's just a little steel spring, making contact there, we screw it on there, it wraps itself on there, makes a tight connection, and now we have a really small loop between the signal and the return, and that's what makes contact between the signal and return on the board. And if you notice on this test board here, conveniently, I have test points that have, let me see if I can zoom in on that. I have test points that are conveniently on 300 mil centers, happens to be the spacing between the signal tip and that ground lead. And so this is one of the principles we teach in our classes, design for test and bring up. And so with that spacing there of 300 mils, that 10x probe fits in there really nicely and kind of stands up by itself. And now we have a really low loop inductance tip that has a highest bandwidth we can get with the 10x probe, basically. Very little radiation, very little pickup. Still a little bit of residual, so it's not perfect, but it's the best we can do for this kind of convenience. And so that's really one of the important tips on getting the most out of your 10x probe.
Okay, good. And another question regarding probing with the passive probe is what would be the improvement I could expect if I went to the trouble of attaching a coaxial connector to my probe tip?
Very good. Yeah. So again, we have another webinar we've done recently where we actually compared the bandwidth of a 10x probe in the 3 different configurations. The case of a really long lead, the little spring tip, and then into a direct coax connection. And generally, you get the maximum bandwidth when you have the coax connection. And for these probes here, I think we demonstrated about a 300 megahertz bandwidth. When we have the spring tip, we generally get about a 200 megahertz bandwidth. And when you use the long floppy leads, depending on how long and floppy they are, the bandwidth is reduced closer to 100 megahertz or less. But again, the other problem, it's not just the bandwidth of the probe, the other problem is we are susceptible to RF pickup, and when we're measuring with the 10x probe a high-speed signal, we have basically made a radiating antenna, and so now we're polluting the near-field environment in which we're doing our measurement by the process of using the 10x probe with the long floppy lead. That's why always a good habit, avoid the long floppy leads, and that's why you want to think about designing your boards, especially in bring up and test, with these special little pads in order to get the to be able to use the little spring tips. You need a return location in close proximity to the signal in order to do that probing.
Okay, all right, good. A question regarding the bandwidth that you were testing to. So the question is basically, it's assumed that the passive probes are, approximately 500 megahertz of bandwidth. To what advantage is there to using a higher bandwidth oscilloscope, like the 2 gig scope?
Right. So we showed a couple of different probes. The 10x probe is one of those, and generally you want to, if you have a system composed of the probe, the scope, and of course the device that you're looking at, depending on if you have a certain bandwidth in your device, you would like your probe and scope system to have a bandwidth at least twice the bandwidth of the signal that you're trying to measure. So if you got a 10 megahertz bandwidth signal, then it's a who cares, anything will work. But if you're pushing the limit and you get a couple 100 megahertz bandwidth signal, then you want to push the limit and do everything you can to reduce the discontinuities, make a clean path so that your probe has a bandwidth at least twice the bandwidth of that signal. And it's the combination of the bandwidth of the probe and the bandwidth of the scope. And it's not just the sum kind of thing, it's 1 over the square root of the sum of the squares kind of thing. And so you want the bandwidth of the scope to be about twice the bandwidth of your probe, and the bandwidth of your probe to be about twice the bandwidth of your device. And that limits the influence of the system. And so if your scope band, if the probe bandwidth is 500 megahertz, do you need 2 gigahertz bandwidth in the scope? No, but you need a gigahertz bandwidth, and that's using the 10x probe. I showed a couple of examples here of the differential probe and the REL probe. The REL probe, that bandwidth is 4 gigahertz, and so if you're looking at fast transient noise, switching noise on the power rail, having you know, the highest bandwidth you can afford in the scope will let you, again, open up that window into what's going on that may reveal to you some hidden noise issues. And so with the bandwidth of 4 gigahertz for the REL probe, the 2 gigahertz in the wave runner is a little limiting. That's why I tend to use the REL probe with my WavePro HD scope, which is an 8 gigahertz bandwidth scope. The differential amplifier, the one I have here, our older one, is only a 500 megahertz bandwidth, where the 1 gigahertz bandwidth of the scope is valuable. Our newest one is a 1 gigahertz bandwidth differential probe, and that's where the 2 gigahertz bandwidth of the scope is really valuable. So it's I call it part of situational awareness, being aware of the bandwidth of your signal, the bandwidth of the probe, and the bandwidth of the scope, so you have a bandwidth of the system.
Okay, all right. 2 more questions. What are the key characteristics we should look for in a differential probe to make the best possible shunt resistor measurement? Okay,
very good. So part of the problem is you got to ask, what's the dynamic range that you want to measure of that current, and that defines the value of the resistor. You want as high a resistance as you can tolerate, given the maximum current through your system gives you a voltage drop, so you want to minimize that voltage drop. So once you establish that maximum current, maximum voltage you can tolerate, that defines the resistance, you're going to be measuring voltages on the order of tens of millivolts of voltage in some cases. And that means you want a sensitivity in the millivolt kind of range. That's the first condition for the differential probe. You want noise level that is low enough to not influence the kind of measurement you want to see. The second, though, is because we're measuring a small voltage on top of a larger voltage, you want to make sure you have good common mode rejection ratio. And for this particular probe that we were using here, when we're on the most sensitive scale, we had a little more than 5-volt common mode voltage that we could tolerate, and we were below that for this example. For the less sensitive scale, we can go up to 50-volt common mode voltage range for this probe, and 60 for our new high bandwidth probe. So those are the 3 most important figures of merit are going to be the sensitivity of the noise, that tells you how small a current you can measure with the shunt method. The second is the bandwidth of the probe, tell you how fast you can see transients. In this particular example I showed, hey, you got filtering of the capacitors on the board, so this particular example showed that most of the frequency columns were relatively low. And the third is how much common mode rejection ratio you can see, and that'll tell you how much you can float the differential probe above ground.
Okay, good, thank you. And the last question is, what are the advantages of using a high resolution scope in terms of measuring emissions?
Right. Well, in this example that we looked at, we're looking at near field. Again, it's the difference between near field and far field. And the smaller signal levels that we're looking for, we want to be able to first have low noise in the amplifier, and generally the higher bit resolution scopes, our scopes, have lower noise figures than 8-bit scopes, for example. And the second is, when we're looking at a signal, in this case we're looking in the time domain, if we wanted to look in the frequency domain, having a higher bit resolution means our digitizing noise floor is lower with 12-bit than if we had 8-bit. And that gives us a little bit better dynamic range when we look in the frequency domain. Both domains, when you look at emissions, both domains, time domain and frequency domain, are both equally important. They give you another, again, everything is about opening up a window into what's going on in your system. And when you look in the time domain, if you have a synchronous signal, as we used here, you can look at what are the currents flowing and the near field emissions from those currents, from currents associated with that synchronous signal or other signals that are synchronous. Oftentimes, if it's repetitive, that's where you can use averaging. And that 12-bit resolution means that you can pull up your signals out of the noise much more easily than if you had 8-bit resolution. You can zoom in on those features. And looking in the frequency domain means you have a little bit better dynamic range because the digitizing noise floor is going to be dramatically reduced with 12-bit. And I will add one comment to it. I've used scopes for 60 years now. I hate to say that. Okay, 55 years. And I have to say, once you try a 12-bit scope, you get so used to never seeing digitizing noise and being able to zoom in on your signals. Once you try a 12-bit scope, you just can't go back to an 8-bit scope anymore. It's just not the same. So if any of you out there have never tried a 12-bit scope, I strongly recommend you go out and you rent one of our 12-bit scopes, you give it a spin, you do that once and you'll be hooked like I have been.
Okay, that's the last question, Eric. So if there are any other closing comments from either Eric or TRS, we can have them now.
Well, we thank everybody for participating and just want you to know we're here to support you. So if there's anything we can do to help, please give us a call. Please reach out to us, and I'm happy to have any discussions and go from there. Thank you.
Yeah, and as a reminder, I will be sending out a link to the presentation video as well as the slides that we reviewed today. So be on the lookout for those maybe by end of day or tomorrow. And we appreciate all of you attending. Thank you for your time.
Great. Thanks, everybody. Bye-bye.
Thanks, everyone.